What's up, guys? Hey, Devs here, and we're back with more LeetCode. We're doing LeetCode every day until I get a job. This one, I just read the problem. This is the first time you notice I haven't solved this problem. You can see my submissions. I have 0 submissions. I'm pretty confident in this one, so we're going to go straight into this one. And this problem is this 707, design a linked list. I've designed a few linked lists back in the past. I've never done it in Java, so I thought it'd be pretty nice to go through this. So we have to design a constructor. We have to design a get given an index, add at head, and then given a value, and then add at tail given another value, and then add at index. So we're given an index and a value. Delete at index given an index. Okay, this one isn't too bad. We'll go ahead and read the problem. It's kind of lengthy. So design your implementation of a linked list. You can choose to use a singly or doubly linked list. We're going to do a singly linked list. A node in a singly linked list should have two attributes, val and next. Val is the value of the current node, and next is the pointer reference to the next node. If you want to use a doubly linked list, you will also need more attributes previous to indicate the previous node in a linked list. Assume all nodes in the linked list are 0 indexed. Okay, so that means the first value is 0, and the second value would be 1, just like arrays, or arrays in Java. Implement the myLinkedList class. MyLinkedList initializes the myLinkedList object. So this is the constructor, and get index, return the value of the index node. If the index is invalid, return -1. Void add at head and value, add a node of value val before the first element of the linked list. After the insertion, the new node will be the first node in the linked list. Add at tail, append the node of the value val as the last element of the linked list. Void add at index, given an index and a value, add the node of value before the index node and linked list. If index equals the length of the linked list, the node will be appended to the end of the linked list. If index is greater than the length, the node will not be inserted. Delete node.index, delete the index node and linked list if the index is valid. So input, yeah, these are the getters. Yeah, no, two. Explanation. They create a linked list, call the constructor. Linked list add at head 1, add at tail 2, 3, add at index 1, 3, or 2. So this should give us the linked list. Yeah, 1, 2, 3. My linked list get 1, so it should return the first index, which would be 2. As you see, we added at the 1 index. I delete at index 1. Now linked list is 1, 2. Get 1. Yeah. Please do not use the built-in linked list library. At most 2,000 calls will be made to get, add at head, add at tail, add at index, and delete at index. Okay. So the first thing we need to do is create a node class. So we're just going to call this class node. Okay. And then in our node class, we want to have we'll have public variables. It'll make everything easier. So public int val, and then public int public node next. Okay, and then we'll go ahead and set the node constructor. So we'll do public node, and we'll set int equal to 0, next equal to null. Now we'll go ahead and create a val, and we'll set val this dot val equal to value, and then we need to set next equal to null, and then we'll go ahead and create one more constructor. And val, and given a node next, we're going to go ahead and set the next. So this dot val, and to keep in line, we'll do this next. This dot next is equal to next, and then that would be equal to val. So we created a node with two attributes, integer value and a node next. So this will keep it tracked with the next node. And then we have three constructors, one with no parameters, one with an integer parameter, and then one with the integer parameter and the next node, right? For a linked list, we do want to have a few parameters ourselves. Kind of keeping the same track, we'll go ahead and set that. So we want to have a public int size, or private. We don't want anyone to access our variables. So private node first, we can do head, and then private node tail. And this should be the only three constructors we need. And then to create a public constructor, we want size to be equal to 0. We want this dot head equal to null. This dot tail equal to null. Okay. So the constructor just initializes the values. You can make it do whatever you want it to do. We can go ahead and set head and tail equal to some value, but we're just gonna go ahead and make them equal to null. Int.get at index. So we want to get at index. We want to make sure if index is less than size. And we want to make sure index is greater than 0 and greater than or equal to 0. And we'll make sure the index is greater than size. Then we'll do this. Else we want to return -1. Well, we'll return in this. So return -1 breaks out that if statement. So to get the value at index, we'll want to keep count. So for int I is equal to 0, I is less than index, I plus plus plus, and we'll make sure to create a list node temp. This will be equal to our head, and temp is equal to, yeah, so if we get index 0, we should be at the head node. And for every I after that, we want to do temp is equal to temp.next. Then we want to return the temp value. So I'll explain this function just a little bit. Given an index value, we want to make sure the index value is greater than or equal to 0. And we want to make sure the index value is less than size. Okay. And if it's less than size, we can go ahead and create a temp variable equal to head if it's in the range we want it to be, right? And then this temp node will be incremented index times to get to the index we want, and then we're going to return the index nodes.val. Pretty self-explanatory. And then add a head int val. So we want to make sure if size is equal to 0, we want to create a, oh, we can do this outside of this guy. So we want to create a node temp. That's a list node over here. We're doing too many problems. So node temp is equal to new node with the value inserted, right? And based on our constructor, this creates a new node with the value we want. Let's separate these out. Okay. So if size is equal to 0, we know that there's nothing in our list, right? So we want to make sure to set head equal to temp, and we want tail to be equal to temp. And then we want to increment size by 1. Else so if size is not equal to 0, we know that there is at least one value in the list. So we want to set temp dot next equal to head. So what this is doing, let me get my Epic pen out. So if we have one node here, and this has our value inside, and we want to add it into a list that has nothing, with the constructor we have, it sets value inside the node, and then it points to null. If we want to add it into an empty list, we have our head and we have our tail. This is the only value in the list, so head and tail would have to point to this node, right? But if we have, for the example, where you're going to have a 1 node, this points to a 3 node, or we can just make it 2. And this one points to null. So tail keeps track of the last node, so it'll keep track of 2, and then head keeps track of the first node. So what we want to do is we want to add the value to the beginning. So we want to create the null, and then we'll set the node, and we'll set the nodes.next value to the head. That's what we did here. And after that, we want to break the heads link and turn it to our first head, to our new head value. So this is kind of what the structure is going to look like if size is not equal to 0. And then we can go ahead and erase all this. So, and then we want to set temp head equal to temp, right? And technically we don't have to do the size in here. We can increment the size outside. Because if it's past value, we create a node and we're going to add it to our list either way. So size will be incremented by 1. To add it tail, it's a very similar operation. So we want to see if size is equal to 0. I'm going to go ahead and create another node. I call it temp. I'm going to set temp equal to, make sure I didn't forget a semicolon anywhere so far. Aha! Forgot 2 semicolons. Semicolons get me, especially when I'm trying to explain the problems. They end up getting me. So now we're at the add it tail function. In order to add it the tail, we'll see if size is equal to 0. And we want to create the new node. So this is going to be equal to new node. And we're going to pass it our value. So we're going to do the exact same operation that we did here. So we're going to set head equal to temp and tail equal to temp. The temp and tail equal to temp. Because this just means that instead of having 0 values, we now have 1 value. And if it's only 1 value, head and temp would be, or head and tail would be equal to the same node. So we want to go ahead and keep track of that. And then else, that means there is not 0 values in our list. And so we kind of want to do something simpler. I mean, not simpler. something different. So we'll hit tail.next. I'll go ahead and draw this out too. So given the same value node, and this points to null, and given our nodes of 1 and our nodes of 2, we have a head pointing here. We have a tail pointing here, and this points to null. If we're adding it to the end, we want it to come after the 2 value. So what we want to do is set tails.next. We want to set that equal to the value node. So now value is just going to be inserted right here. And then it's still pointing to null. And then we want to make tail point to the new last node, right? So we'll set tail equal to the value node. So tail.next is equal to temp, and then we want temp tail to be equal to temp. Right, so we've successfully added at the head, added at the tail, and we've also gotten the value. So now time to add an index. This one's a bit different than the other two operations. So first thing we need to do is make sure the index value is in the range, right? So if index is greater than 0, greater than or equal to 0, and oh, don't do this. So add at tail, we want to make sure to increment size. So size plus plus again, because we added one value into our list. We want to make sure to keep track of that. And to make sure I don't do it again, we're going to do size minus minus. Because if we delete a node at the index, we want to make sure to keep track of that. And we want to make sure index is less than the size. Right? And if the index is valid, that's all the if statement's checking, is if it's in the range that our list is in. We can go ahead and do the same for loop. So for int I is equal to 0, I is less than index, and I plus plus. And if we're given this, if we're given 1, and then our value 2, and this points to null. The indexes of these would be, this would be index 0, this would be index 1, and head would point here, and tail would point here. So there's 3 special cases that I want to do. This might not show it off too well, so we're going to go ahead and add the oh, that's a 2, and we're going to add a 3 node here, and this points to null. So tail points to 3, head points to 1, and we have a node here with a value inside of it, and we're gonna initialize this soon, and this is pointing to null. So if there's 3 different operations. If size is equal to 0, we want to just set head to point to the value and tail to point to the value. The same operations we did to add a head and add a tail. And then there's 2 other cases, edge cases that we want to look out for. If we're adding at the beginning, so if we add at index 0, we want to make sure to add head, to add the head there. And then if we're adding at the tail, we want to make sure to keep track of that. So tail would be size minus 1. this would be the index of it. So if we add an index 0 and if we add an index size -1, we want to make sure to move the, or if we add an index size, yeah, I almost messed that up. So if we add an index size, that means we're adding at the end of the list, right? We're going to make sure to keep track of that. So there's 3 different special test cases, and I'll be sure to show you all those. So if index is equal to 0, we want to be sure to add at head. I'm pretty sure that's add at head the value, right? Else if index is equal to and we'll go ahead and return here. Or, well, we'll just do an else if ladder. And if index is equal to size, we want to add at tail of the value. So that way we don't rewrite this code. I will just go ahead and call these functions inside of our add at index function. Because we add at index 0, we want to be sure to reroute the head correctly. And add at head does implement that correctly. And then if the index's size is 0 and we want to add at index 0, it will be sure to handle that accordingly because we wrote the code for that, and it'll set head and tail equal to the temp value. And then if it's neither of these, we want to make sure to do the final else statement. And this is when we'll do our for loop. So for int I is equal to 0, I is less than index, and then I plus plus. We'll create a temp. So we'll show this off now. So if this is index 1 and this is index 2, and this would be index 3, and then our size, if you count the array, or not the array, the list, the nodes we have drawn out here, there's 3. So size would also be equal to 3. So if they want to add an index 0, it will add the value in front of the list here. And then if they want to add it at the end, it will add the value here. Right here, and then go next. So we've taken care of those 2 edge cases. But the only other case we have is if we want to add inside the array. So, or add in between 0 and size, right? If it calls one of those indexes, then we want to be sure to handle it accordingly. So the way we would want to proceed with this is index 1 keeps track of our the node. Like if we passed, say, we want to add at index 1, right? What we would want to do here is we want to break this link, add value here, set this link to here, and then set this link to here. So we need to keep up with, I think it's probably 2 total nodes, or 3 total nodes, including our value node. So we want to keep up with the previous. And we want to keep up with the next node. That way we can link them up accordingly. Or we might not even need to keep up with the next node. So I'm going to do node temp is equal to new node temp. new node with the value. And we want to be sure to increment size plus plus. The reason we're not doing size plus plus out of the if else ladder is because if we call add at head or add at tail, once it completes this function call, it'll break out, come back to this function, and we don't want to increment size again. So we only want to increment size if we come inside of the else, right? So we created our temp value, and then we want to create our node current value equal to head. Now that we have the head node, I'm trying to think of how we would want to do this. So once we have the value, we can set value equal to that. Okay. So we're going to call this the iter node, make it equal to head. And then we want to iterate to index -1. And then we can go ahead and do iter is equal to iter.next. And what this is going to do for us is let me draw this back out. We'll have a current node here with head, and it's going to point to the 0 value. So if we want to add at 1, it will not call this I is equal to 0 and I is less than index -1, and our index that we want to add at is 1. So it's going to break out of this function here. And then once we break out of this function, we want to go ahead and set temps.next equal to iter.next. And then we want to make sure to set iter.next equal to temp. So we can draw this out here. So it takes this value here. It breaks the link we created. And then it sets temp, because this is our temp variable. And it sets its next link equal to the currents.next. So now they're pointing to both pointing to the next node. And then we want to be sure to break this link of the currents, and we would create, or our iterator, we didn't call it current. That's probably a little bit confusing. So we want to create our iterator, and we want to set its next link equal to the temp value. So we'll break that link and then create it here. And now we've added 1, and our new size would be 4. And our new index values would be 0, 1, 2, 3, and then 4, like so. And I'm pretty sure that's the correct logic. Go ahead and erase this. And then we can go ahead and go to the final, delete at index. So to delete at the index, we got to make sure the index value, or the value of index is in between the value of index is in between the range we want, right? So the range we want would be from 0 to size. Or it might be like this. This might be easier. It's just size -1. So we want to make sure that if index is less than, greater than or equal to 0. Oh, what do we do, fellas? I don't know what I clicked to get there, but we're going back to the delete at x. So if the index is 0 and if and we want to make sure the index is less than size. And if it's size -1, it's still going to be less than size, right? And if it comes inside this if statement, we want to make sure to make size minus minus at the end. And we don't want to decrement size if we are outside this if statement, because that means the index value is not in the range we want. And then from here, we have a few kind of like the last problem. We want to be sure to we can check if size is equal to 0. Well, so if size is equal to 0 and if index is 0, this statement will end up being false and it will break out the if statement. So we've taken care of that test case because we can't remove out of an empty set, right? So we do want to check if size is equal to 1. Because if size is equal to 1 and we're removing from index 0, then we know that we know that we're moving from a single element list. So right now we're doing case 1. For case 1, we have a list that kind of looks like this, where head and tail are both pointing to the node that's pointing to null. So if size is equal to 1, we only have one node in our list, and we'll be sure to set the head equal to null, and we'll be sure to set the tail equal to null. Else if the index is equal to 0, if size is not equal to 1, then we know that the index is not index. We know that size is not 0. We know that size is not 1, and so we know there is more than one element in our list. So it has to be 2 or greater at this point, right? So this would be case 2. And so we have a head value pointing to this node, and we have a tail pointing to this node. And in this case, we want to be sure to reroute this accordingly. Okay. So if index is equal to 0, we want to set head equal to head dot next. So this means if we made it to this if else blocks, that means that size has to be greater than 0 and it has to be greater than 1. So we at least have 2 elements. And then so we want to break this head link, and then we're going to set head equal to the next value. And so this node right here will be garbage collected by Java, so we won't really have to worry about that. And we only have to set head equal to the head.next. And it's a bit different if we're deleting anywhere in the middle of the list. So case 3 would be we're deleting a node from the list that is more than 2 elements inside, and the node is possibly past head. So we know our link list would kind of maybe look like something like this, right? And this one points to null. Like we said, we have the tail pointing to the last node, and then we have head pointing to the first node. So we know it can't be the first value, because we've already checked that the list is has a greater size than 1, and that the list is less than so we know we're not going to remove the head value, and we know that the list has more elements than 1, so there's at least 2 or greater. So there's 2 possibilities. We're going to delete a node in the middle, or we're going to delete a node at the end, right? So this case 3 has a case 1 and a case 2, right? And case 1 would be we're deleting it from the middle of the list. And so we'll write that code next. So else we want to create a node called temp, make it equal to head. And then we can go ahead and iterate. So for temp, not temp, for int I is equal to 0, I is less than index, and I plus plus. And then we want to set temp equal to temp dot next. So we can do -1 again. So in the case that we are trying to delete the index at 1, so right now I'm writing the index values. We're deleting in the middle of the list, and we'll be sure to get the node behind it, right? And what we would do is we would set, so temp would be pointing to this node as well, or referencing this node. So we want to set temp dot next, so this arrow, equal to temp dot next dot next. So what it does is it will break this link and route it around this node and point it to here. And this node will be deleted by Java's garbage collector, since there's no reference to it anywhere. And so you can imagine after we relink them, it will delete all of this and keep the link we created. But we can go ahead and go back. So there's one more case we want to look out for, is that if we're trying to delete the node at the tail. So in here, in the else, we want to check one more if statement. So if temp is equal to tail, or temp.next is equal to tail, that means the temps.next and tail is the same node. And if that's the case, we want to set tail equal to temp. Okay. And then we can do the operation that tail.next is equal to tail.next. Not tail, temp. Or tail would not work for this. So temp is equal to temp.next. And that should be the full linked list and all the methods that they want us to implement fully implemented in Java. I'm pretty sure my logic is right, but we can go ahead and we can scan it for semicolons, because we don't want, because it'd be very sad if we missed a semicolon again. Yeah, I don't think I missed semicolons. Let's see if we have a error. Oh, did I say int equal to 0? Where did I do that? But we don't want to set int equal to 0. We want to set this. This is this values, and then we want to set this dot next. So okay, forgot a semicolon. I did forget a semicolon. in this for loop. There we go. So it successfully ran for the test case they gave us. I'm going to go ahead and run it for all cases. Yeah, there we go. 7 milliseconds runtime. It beats 83% of the 83% of the others. And we can see this guy designed it in Java, so we'll take a look at his. Here's his code. Okay. Private static class. No. Okay, I don't know too much about classes inside of classes. It looks like they, I mean, it looks like it works the same as the class we created outside. So ours is a bit blockier because we check if the index is inside it, and then we do the loop. And what they do is they check to see if it's inside the value. Private int void class by linked list private get node at index. Okay, I see what they did there. So if the value, instead of checking if the value is inside the index, they check to see if the value is outside the index, and then they return. That way, this block of code is not nested inside of this if statement. It just kind of makes the readability a bit easier. But I'm happy with this. All in all, I'm very happy with the way this turned out. And his is 6 milliseconds runtime, and ours is 7. Let's see if there's another Java. Beats 84%. Looks like theirs is about the same. Inner node class. Okay. So we created our node class outside, but they created inside. I don't really know too much about nested classes, but it looks like it's just when a class is created. So when a class is created in the heap, it also creates this class blueprint available for it to use. So I think this just means you can't use node outside of the linked list. I think that's kind of what that means. I don't know too much about the nested classes. But anyways, we created a linked list from scratch. I'm very happy with my solution. This is kind of reminiscent to the linked list I've created in C++ in the past. By in the past, I think that was, it was coming up on 2 years now. Next May would be when I took the final for that class. And it'll be 2 years ago from then. So I'm glad to say I still got it, and it's kind of engraved in my memory, following following all the methods they wanted to add. This might have been nice to do at the beginning of our linked list journey, but as you know, it's day 14, so it's the end of our linked list journey. So I think tomorrow we're going to do a different subset of problems and maybe do those for 2 weeks. I did say we were going to do arrays and linked list, but I ended up just only doing linked list problems because we were just kind of on a roll. But I think we got linked list down, and nodes are fairly friendly to me. There's a few other problems I think I should be able to do with linked list. Delete node in a linked list. I mean, this is there's a singly listless head, and we would delete a node in it.
You're given the node to be deleted node. You will not be given access to the first node of head. All values of the linked list are unique, and it's guaranteed that the given node is not the last node in the linked list. Delete the given node. Note by deleting the node, we do not mean removing it from memory. We mean the value of the given node should not exist in the linked list. Nodes should be decreased by 1. All the values before nodes should be in the same order, and all the values after nodes should be in the same order. So you're given the node of it, so I think you just want to copy the next values. But I think I should be able to do this problem. Odd even linked list. What is this one? Okay, so we're just rerouting those. I think if we create a if we create like two list objects and hold all the even numbers in one and all the odd numbers in another, we should be able to rebuild the linked list fairly easily. I think I could do that one. The flatten a multi-level doubly linked list problem. This one I feel like I could do. It's a bit complicated, but given this, the node is a doubly linked list, and it also has a child, so it can break off and point to another linked list. It wants the initial what's it called? Multi-level doubly linked list. It wants the initial list that looks like this to read like this. So it wants to go 1, 2, 3, 7, 8, 11, 12, 9, 10, 14, 4, 5, 6, as you can see here. So we could just kind of loop over, we could just loop next, and then keep up with the 3. And if 3 and we can check if they have a child node in each. And since 3 has a child, we'll want to go ahead and create a node that keeps up with this list, and then add dot next, 3's dot next equal to this, and then we'll keep up with the 4 as well. And then once we get to the 10, we'll set 10's dot next equal to 4, and then same with the bottom. We can probably use a recursive function because once we get here, the problem is broken down into a smaller problem, and then once we get here, the problem is broken down to a smaller problem. And so I think I could do that one as well. This is the design linked list that we were given. Split linked list in pairs, linked list components, middle of linked list. This one, yeah. So I'm guessing they want us to do this in a first pass. So probably the easiest way to do this is to count the lists and then go through, but I wonder, simple and clean, slow and fast pointers. Simple solution for beginners, 2 pointers, linked list, C++ Java. Let's see, slow is equal to head. Okay, yeah, so that makes sense. I didn't think of that at first. But they have a first node, and then both of them are pointing to the beginning, and this will be incremented by 1, that will be incremented by 2. And then as soon as the fast node reaches the end, the slow node should be at the middle. So then fast would be incremented by 2 again, giving you 5, and then the slow node would be incremented by 1, being at 3. We know that 5 is equal to the last. Okay, that one's not too bad. And then, anyways, I'm kind of going on a tangent of other linked list problems I should be able to do. I might later on, if I get stuck and can't solve a problem or spend too long solving a problem, I might go back and complete one of the problems I just talked about. But we can go ahead and take a look at the go to the top. We have two filters. It's in Java and it's a linked list. So I'm thinking that we can do maybe binary tree, not binary search. We can do trees, or we can also do stacks. Both of those have pretty good problems. Stack is another fairly simple data structure. Or we might do like stacks, then queues, and then make our way up to trees. And then we need to learn, I need to learn about heaps. Heaps would have been very useful for plenty, a couple other problems. Merge case ordered list, it's a heap problem. That one would have been easier with using a heap. Top K frequency elements, that also would have been good with a heap. We can do some array problems, and strings are fairly, I'm not too good with string manipulation, but that one would also be a useful problem. But I'm thinking we might do a few sorting problems, or I'm thinking we're gonna do trees or stacks next, one of the two, and do those for the next 14 days, and then the next 14 days after that we'll also do the other. I'll kind of play it by ear and see what I'm thinking. But anyways, that's gonna be it for the day's problem. Of course, we completed the let's go back to the problem we completed. Linked list and status is solved. We can see all the linked list problems we've done. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've done 12 linked list problems. I'm fairly happy about that. Well, where's the one? Where's the design linked list? The very last one. So we did problem 707, design linked list. We just designed our own linked list using the nodes that we have been using, or the list nodes that we've been using for the past few problems. We design our own abstract data type called my linked list, and it has fairly simple operations. It doesn't search. The only search it has is it doesn't have no search function or anything like that. It just adds. It has a get, and it adds at tail, adds at head, adds at the index, and it deletes at the index. So anyways, I think that's gonna be all for today's video. I do have a good bit of homework to do. I don't know how long I've been recording now, but I'm guessing it's been a decent minute. I've been yapping for 12 minutes after we completed this problem about other problems I could do and what we're possibly gonna do in the future. But I have a little bit of homework I need to get done tonight. My girlfriend gets back from work in 2 hours, so I want to be sure to get that done before she gets home. And then tomorrow I have school as well, and I have a few other homework assignments I got to do before Wednesday. I also have a test Thursday, but I took off of work Wednesday, so there should be another. I mean, I'm gonna post a video every day. That's the plan, anyways. And then, but I have some stuff I got to do in between it, so it might be easier problems coming up because I have like I said, a test Thursday. But after my test Thursday, and after work on Friday and Saturday I'm off, so I'll probably try to do a hard problem. But we did another medium problem, just building our own linked list. If you have any questions, comments, or concerns, be sure to leave them down below. I hope y'all stay blessed, stay healthy, and I'll catch you on the next video. Hey Devs is out.